Okay, so we're going to be looking now still at momentum, but we're going to be thinking a bit more in terms of vectors. So that is to say, the initial speeds and our final speeds are going to be vectors rather than simply left and right. They're going to have a bit more of a 2D perspective to them. I'm going to split this into two parts, so this actually won't be that long. It shouldn't take you too long to watch this video and try the questions at the end, which is always nice, which should mean you've got plenty of time for it. So first off, I'd just like you to try and write the following two principles, and this time make sure you write them using the correct notation. So again, I'm looking for precision here in the answer, because you should really already know these formulas, but I just want to double check you can precisely and without error write the expressions using the correct notation. So give that a go. Before I write the answer, you can pause the video and check that you can do this. Okay, so then let's call these 1 and 2. Number 1, the impulse momentum principle. This is saying that I equals mv minus mu. Also sometimes just written as m times v minus u. But that's not the vector version, so just make sure we do this properly. I is a vector, m is a scalar, v is a vector, u is a vector. V and u are both vectors. Okay. And then the conservation of momentum principle, I'm going to write it fully now. So let's say or let's not even enumerate things. Let's just keep it some arbitrary number of objects. M I times ui is equal to the same number of objects, where I is some index on the objects, like this. And then again, u is a vector and v is a vector. Okay, if you just did it for two objects, that's fine, but just remind yourself that technically speaking, it can be for any number of objects. And I've not put any notation below or above the sigma, which is fine. This is just a mathematical shorthand to say some quantity of objects. As long as they're indexed in some way, I know which one is object 1, 2, and 3. Who knows how many I've got? Doesn't matter. The principle still holds. Okay, that's it. So as long as we've got that down, then we're good. So just not too many examples to look at here. It's going to be conservation momentum and impulse momentum principle using some vectors. Okay, so our first example, particle of mass 0.2. It's got a velocity 10I minus 5j. I'm going to immediately write that as an actual column vector, minus 5. It receives an impulse 3 minus 2. Find the new velocity of the particle, that is to say, find v. Nice and easy. We use our impulse momentum principle. And again, these are vectors, right? Instead of doing an arrow, I'll just do a simple line. So there we go. We've got the vectors there. It is a good habit to indicate which things are vectors and which aren't. Perhaps in the case where I've explicitly used an equals, u equals 10 minus 5, it should be obvious. So maybe you can skip doing it, but if you're one for consistency, sometimes it's nice to just make sure you label your vectors accordingly, so you never forget and you get used to the idea. So then we've got 3 minus 2 equals 0.2 times v is our unknown. In fact, let's split this up. So 0.2 times v minus 0.2 times 10 minus 5. And then I'm just going to fast forward, and we get this just by manipulating our vectors a bit. And if we fast forward one more time, oh, hang on, that 10, no, that's correct, but too much fast forwarding there. 0.2 times 10, that's 2, should be 5 minus 3. Multiply both sides by 5, we get 25 minus 15. Yeah. Okay, and that's it. Find the new velocity, that's acceptable. We can just write it then as a vector, because velocity is a vector. If you were asked to find the speed, that would be the magnitude of v. In other words, the square root of 25 squared plus the minus 15 squared. Okay, which of course is just 15 squared as well. So speed takes a little bit of extra work, but not that much extra work. Let's look at another example. So we've got an ice hockey puck, mass 0.17. So I'm taking notes as I read the question. Receives an impulse q. So my impulse is some value q. Newton seconds. Q. No, notice q is in bold. So q is itself a vector. So I'll just be taking note of that there. Within the textbook, the bold is there for a reason. Just remind yourself of that. That is actually a vector. So I is basically q. Immediately before the impulse, the velocity of the puck is 10.5. And immediately afterwards, its velocity is 15 minus 7. Find the magnitude of q. Right, so that's what we're being asked to find. What's the magnitude of q? And the angle between q and I. We'll get to that in a moment. So magnitude of q. So let's use the impulse momentum principle. M times v minus u. And then let's fast forward. So we get 0.17 times 5 minus 12. And that's equal to, if we then use a calculator, we'll double check the book, 0.85 minus 2.04. Okay, so that is, that's q, or I, same thing. Therefore, the magnitude of q, that's using what we just talked about at the end of the previous example, that's going to be the square root of 0.85 squared plus 2.04 squared, and I won't bother with the minus because I'm squaring it, and that equals 2.21. Okay, so we've answered that question. The magnitude of q is 2.21, and I'm also just going to note again what q itself is, because we're going to need that for the second part. There. So what is the angle between q and I? Let's just make sure we draw the diagram so we don't confuse ourselves. So I, remember, is a unit vector going in this direction along the x-axis. That's our I. And q then, just we want to make sure we draw that in the correct place relative to the I. So it's got positive on the x and negative on the y. So we know that it's going to be doing something a bit like that. Oh dear, that should be a straight line. A bit like this. Okay, something like that. That's q. So then we just want to find the angle. So that's what we're being asked to find. What is that? And to do that, just create a triangle, effectively. Right, so we're effectively creating our right angle triangle. We know that this distance here is 0.85. We know that this distance here is 2.04. And now I've just written it as a positive value because now I'm just thinking of the geometry. So I'm talking about the length. And you just want to do arctan, Right, opposite over adjacent. So what is arctan of the opposite over the adjacent? And we'll stick to degrees just because the textbook's given it in degrees. Technically it wasn't specified. In this case it's 67.4 degrees. Okay. Maybe a note on that actually, radians versus degrees. In pure mathematics, we tend to stick with radians when we get to the advanced level. Within mechanics, it's almost, I would say probably at really advanced mechanics, you go back to, you might also use radians, but it happens maybe much later. And I guess within engineering and at least A-level mechanics, you tend to stick with degrees again. So it's you get kind of used to when degrees are the convention, when radians are the convention. Within mechanics, for now at least, and for most of it, by convention or by default, I should say, we'll be working with degrees. So if you're not told, we just work with degrees. So you need to be obviously fluidly working between the two. That's particularly the case for if you're going to be getting many questions which flip from pure to mechanics. Try and remember which you're working with at all times. It should be made clear really if there's any ambiguity. But yeah, stick to degrees mode for while we're working mechanics now. Cool, so that's it. That's that example done. I think we've got one more. Okay, no, I was mistaken. We don't have one more. As I said, it's a short one because it's part one of a two-parter, just to get you into the groove of things. So you should have plenty of time. Have a go at these three. And since they are sort of foundational level questions, focus your effort on really writing the notation out formally and properly and making sure that you've understood it well. It's not just about getting the number. So focus, see if you can use the time that you've got, since you've got quite a bit of time. Write out things properly, make it clear which things are vectors, which are not. Things are going to get harder, so you want to be able to distinguish things and get used to the notation accordingly. Cool, so have a go at those. You can pause the video, and when you're done, look up the answers in your book.